Okay, so let's continue then. So we have now shown how to, a small example of internet working where an IP packet is going over several networks. And we saw that the one thing that was needed was an address translation, or address resolution. If you remember when we started today, we talked about web browsing, that there is an internet name and there is an internet address. And these two things point to the same thing, but they are meaningful at different layers. So humans, for instance, would prefer not to talk about with IP addresses. So if I want to go to the Chalmers website or some other website that I perhaps never been to, I can almost guess what the internet name of that web server is. So for humans, it's very good. However, it's not useful for the lower layers in the protocol stack. So we need to translate between internet names and IP addresses, and we use DNS for that. Now, in this example here, we needed, here, at some point, the IP layer needs to tell the link layer below it where to send the information. So in this case here, we wanted to transmit an IP packet over Ethernet. And then we need to tell Ethernet about the Ethernet address of the destination, so the physical address. So there is a mapping between IP addresses and physical addresses, right? And this is actually what we started with here. Okay, sorry for this. Here, this table needs to be populated at each node. Okay, so the server, for instance, needs to, in its routing table, it needs to figure out the physical address of the nodes which is attached to the same network as itself. So the server, for instance, needs to know the physical address of the workstation and the router. So the server here, it knows its own physical address, right? It could just ask its interface card, what is your address? What is my address? Right? But how does it know W and R? Right? And this it needs to figure out. So there is a help protocol called Address Resolution Protocol, ARP, that does this for the IP layer. So the IP layer asks the ARP protocol to figure out the physical address for an IP address. Okay, so, and again, you can read about this and you can almost play around, maybe not interact directly with ARP, but for instance, if in this computer, if I want to figure out what network interface cards do I have here, I can use a command on the Mac that looks like this. It's called network setup, and then there is a long qualifier to this that says list all hardware ports, and then I hit return. And these are the hardware ports or network interface cards which are available on my machine here. It has a Bluetooth modem, right? It doesn't have a physical Ethernet address, okay, because it's not such a technology, right? So let's skip that. But it has a Wi-Fi port here, and it's called EN0. It's the logical name of that network interface card, and has an Ethernet address here, E0, AC, CB8, and so on, right? We also have a Bluetooth port here, and has this Ethernet card. There's a Thunderbolt, and has this one. There's a Thunderbolt bridge, and it has no address. Okay, that's it. Okay, so now I know my own physical addresses, depending on which device I want to use. But how, if I want to figure out what the IP address tied to this is, I can query my own table to figure this one out. So the name for that, okay. So I didn't have it in, it's called IP config, I believe, and then get interface address. And then I take one of the interfaces, maybe the Wi-Fi port here. And then, oops, what did I do wrong?
The argument should probably be get not address.
No. Get.
Maybe without the dash?
Yeah, let's try that. Hey! Okay, so the IP address of the Wi-Fi in my laptop right now is 10.0.139.77. Okay, and if I look at, for instance, let's see, the Thunderbolt here, EN1, for instance, I get nothing because it's not connected. Okay, so when I plug this into my office, I have I plug it in via a screen, and then I have a wired Ethernet, and then I will get an IP address for this. So I can have several IP addresses, right, at the same time. But a card only has one. A card could also have multiple IP addresses. But once I have an IP address, it uniquely identifies a card, a port, somewhere. Okay. So we won't go through the ARP protocol here, but there is a way, just as DNS, to figure out protocol, how to translate between addresses. So if you bear with me, okay. So we ended up here. So we now saw a practical example on how we can make a small network look simpler for the higher layers. Okay, so the OSI reference model sometimes is drawn like this, and how we can think about this is that here we have the end nodes on the left and the right hand side. It has a full stack, right, with all the layers. The intermediate nodes here only has up to the network layer because it doesn't need any more, right? And how one can think about the intermediate node here is that we have a line going down here. So we have one physical and data link layer which points in this direction, and then a network layer consisting of two parts, one which is serving this part and one which is serving that part. So data goes up here and moves over down and then go down here. That part of the data link layer talks to that part. Okay? That physical part talks to that physical part. And then data goes down here and then up here, down here, like this, right? So these intermediate nodes, we can think of them as they have some type of split in the middle here. Two separate data link entities, two separate physical entities here. A common network layer that can move data from one part to the other. Okay? All right, so let's now get down and dirty in the physical layer, because here is all, well, my background is in the physical layer, so I like it. So I'm very excited about things going on here because they are difficult and interesting. So I will talk a little bit about the physical layer here now for 2-3 lectures maybe, and so forth. And after we're done with that, then you're able to start with the project, no problem. As a matter of fact, we have a lecture tomorrow also, and after that you should be able to start to work on your project. Okay, physical layer. Here, people that work in the physical layer also have a model for how communication is done. And the physical layer, its purpose is to transfer bits from point A to point B over a physical medium. That's it. There's no concept of network or routing or things like that here. It's conceptually a very simple problem, but it's also very difficult, so that's why it's, or could potentially be very difficult. So there's a lot of people working on physical layer. Now, for people that are trained in physical layers, when they enter into a course, this is the type of model for communication they see. So we have a source which is generating bits, and we have a sink which is consuming bits. And the purpose of the physical layer here, there is one physical entity here, it's called the transmitter, and one which is called the receiver, and they are interconnected with something called the channel. Okay. The purpose of these two blue boxes here is to move bits from here to here. That's it. Okay. And we have some type of cable or radio channel or something like that here. Okay, we call that just channel. this channel is not perfect. Every physical channel has some problems, right? And one problem, the simplest problem we can think of, is that it adds noise to the transmitted signal. So the transmitted signal here from the transmitter is disturbed by this noise. So the receiver sees a noisy version of what was sent. And the purpose of the receiver is to take this noisy observation and then produce bits. And hopefully these bits are the same as the bits that were transmitted. Sometimes they're not. Okay. So one performance metric for physical layer communications is to calculate what is the probability that a single bit is in error here. That's called the bit error probability. And the whole purpose then is to design things in the transmitter and receiver to minimize the bit error probability, and at the same time, during the constraints which is given by the channel, right? What type of signals can we transmit? What power levels can we use? What is the strength of the noise and so forth? Okay. So we want to do the best possible job we can do with the channel which is given to us. Okay. So the channel is outside our control. We cannot do much about that. It's what it is. And we should do the best with that. Okay. So there are three. This is called the Shannon's communication model. And Shannon is the founder of a scientific field called information theory. So he was very active in the 30s, 40s, 50s, maybe a little bit into the 60s. So he wrote his most famous paper in 1948. So he's the founding father, and it's like for all people that do communications, he's like Newton for people that do mechanics. Okay, so the founding father in this case of the field. Okay, last year there was this celebration of 100 years after his birthday. So he was born 1916. Anyways, what he did is that he said, okay, we can take this transmitter, we can split that into 3 boxes, and we have a receiver that can be split into 3 boxes, and we can design the transmitter and receiver such that given a channel, we can minimize the error probability here. Okay, so he said it's possible to do this. We can do this optimally. Okay, and then what he said, okay, is that we have these 3 boxes, and the purpose of them is the following. Is the first one is called the source encoder, and what it does is the data compression. So here there's a number of bits coming in per second, say a megabit per second, for instance. And the source encoder can compress that down to a lower rate, typically, so maybe 100 kilobits per second. Okay. You know, you all probably work with like a zip function, or so compressing text files and so forth. You can see you can reduce the number of bits in the text file quite a lot, and you can recover them without loss. Okay, so the source encoder basically do data compression in order to minimize the number of bits we need to transmit, because transmitting a bit is costly. Okay, so we don't want to send any bits unnecessarily. The second block here is called the channel encoder, and its purpose is basically to be able to detect and correct errors that occurs. So here is some information bits coming here. And these needs to be transmitted over the channel, and hopefully it should be the same information bits here. What the channel encoder does is it adds some control bits, some check bits to the information bits. So here we have actually more bits than what we had here. So if there is 100 kilobits here, maybe there is 120 kilobits per second here. And then these bits are then being transmitted over, and there might be an error here. So here the error probability might be 1%, say. And then the channel decoder then can fix many of these errors. So maybe the error probability here is 10 to the minus 6. Okay. So it's for error control. The modulator, its purpose is to take bits and represent them with waveforms or something that fits the channel. So if it's a fiber optical channel, this will be, it will be the output of a laser. If it's a radio channel, it will be output from an antenna, electromagnetic wave. If it's in a cable, it will be also an electromagnetic wave, but with different properties. Right? So here one can think of this as a digital to analog conversion. Right? Bits, waveforms. And the demodulator is the inverse. It's from waveforms to bits. But this D to A and A to D are different from what we usually are used to when we talk about sampling and reconstruction. They are designed differently. But the overall purpose is to go from bits, which are numbers, ones and zeros, to a waveform, maybe a sinusoid of with some properties. Okay. So the black things here are bit streams, and the red ones here are analog waveforms. So let's talk about the simplest setting we can think of, that we want to transmit 1 bit. Okay. If we can transmit 1 bit, we can repeat the process and transmit 2 bits, right? So so eventually we want to transmit many bits, but the simplest we can do is to transmit 1 bit. And how are we going to do that? Well, now we're going to skip these blocks here and just look at the problem of transmitting 1 bit here and reproducing that bit here with as low bit error probability as possible. That's the task. Okay. And what messes things up is the channel. That's noisy. Okay. So the simplest thing we can do is that we take a bit represented by this variable m. M is a binary variable. It could be 0, 1, or in this case 1 and 2, or it could be -1 and 1. It doesn't matter. The only thing that matters is m can take on 2 distinct values, and that's it. So it's a binary variable. And whether it's 0, 1, 1, 1, 2, or -1, +1, it depends on what's convenient for the math, right? But it has no fundamental meaning. And the modulator is a very simple device. It has 1 bit input, and it should output a signal. So how many signals can it output? 2, right? Because there are only 2 inputs, and it's a deterministic thing, so there is no randomness in here. So depending if the bit is 1, then it outputs a signal S1, or if it's 2, then it outputs the signal S2. So 2 signals we can transmit. So S here is the transmitted signal. It's either S1 or S2, nothing else. Okay, the receiver, the demodulator here, observes the received signal R, which in the simplest case, the channel just adds noise to it. In general, the channel distorts the transmitted signal in various ways. It could be filtering or nonlinear distortion and so forth. But the simplest channel we can think of, which is non-trivial, is one which just adds noise to it. So there is some noise here which is added by the channel, and we don't know what the noise is. It's something due to random movement of electrons in conductors or whatever. It's something. And then the received signal that the demodulator has to work with is the transmitted signal plus noise. Okay. And the purpose of the demodulator is the following. Given an observation R, it looks at the signal, received signal. It knows what the possible transmitted signals could be. That's known because this is a design thing which is done before anything is transmitted. It needs to figure out what M is. And this is called detecting or guessing or deciding. Okay. So the purpose of the demodulator is, given R, knowledge of S1 and S2, figure out the value of M. Clear? Okay. So now we will start to use the whiteboard more and more, because now we're starting to talk about math and signals and so forth, and it's more easily done on the board here. So we're dealing here with binary transmission. So binary means that we transmit 1 bit. Okay. The received signal is R of t, which is S of t plus N of t. Okay. So this can be of 2 forms, depending on the data that was transmitted. It's either S1 plus the noise, and this happens when m is equal to 1. Or it's S2 plus the noise when m is equal to 2. Okay, now for a simple example, let's assume that S1 is just a square pulse like that, with some duration t seconds, say. And for the sake of this example, let's say that S2 is just a negative of S1, so it's a negative pulse with the same duration. So one of these gets selected at the transmitter end, but at the receiver, this selection is unknown, right? So the receiver doesn't know which one was transmitted, because if it did, it knew the bit, right? So that's not the problem. So the receiver knows that either was this one or that one, and then it knows its observation, R of t. So suppose the received signal looks something like this. Okay. What should the receiver do? How should we form our guess of m? And let's call the guess m hat. So the hat here has nothing to do with Fourier transform or something like that. It's just I use this to say it's an estimate or a guess of a variable, which is m. Okay. So what is m hat? What would be the case in this case? How should we arrive to this? It's not so easy, right? Now, suppose it was like this instead. What should we choose then? S1. And why is that?
Because it's very similar to S1.
Yeah, so it's similar to S1, right? If it's like this then, it's harder, right? But we're on the right track. We want to find the signal S1 or S2, which is the most similar to what we have observed. Right? And how can we do this in a structured way? Because, I mean, obviously not a human is not going to look at this. We want a machine to figure this one out. Okay. And the main tool for doing that is to define a distance between signals, which is a similarity metric. Okay. We would like to, given a signal, an analog waveform, compute the distance of this analog waveform to the various possible transmitted signals, S1 and S2. Okay, so let's define distance between 2 signals, right? I mean, obviously we know what the distance is between 2 points. We just take a ruler and measure it, right? But how can we do that when we are talking about signals? To do that, we take a slight detour and do a few definitions and then explain why these definitions make sense. First of all, there is something called an energy of a signal, And that's simply, we take the signal, square it, and integrate that. And then we get a number. And that number will be large when we have large amplitudes. It will be small when we have small amplitudes. The longer the signal is, in the duration of it, the more energy it contains, right? So both amplitude, that is amplitude like this, and extent in time determines the energy. Right? And we will deal with complex valued signals also. So we just take the magnitude squared of this. Okay, so that's the energy. Now when we have the energy, so if we have two signals, we can define what's called an inner product between them. It's also known as the scalar product. And we here have special angled parenthesis, which has a specific meaning. And then we have two signals here, x and y. And then we calculate this integral here, x times y conjugated, integrated for all times. The value of the integral is a number, right? A complex number. And that is the inner product of this, between the two signals. So the inner product is a mapping between two signals and a complex number. Now we see that the norm, this is called the inner product. We can form something which is known as the norm of a signal x by taking two vertical bars here. That's notation. And what that is the square root of the number we get here when we have x, the inner product with x with itself, which is this integral, which if we set in the definition of energy, is just the square root of the energy. The norm, we can interpret that as a length. It tells us the length of a signal, or the size of the signal, if you like. Okay. So now when we have the size or length of a signal, we can compute distance between two signals, right? Because the distance between 2 points in space, this point and this point, is the length of this, right? So if I can calculate length, I can calculate distances. So how do we do this? Well, we take the distance between x and y is the length of the difference between x and y. Okay, and what is this? Well, it's the square root of this integral. And the integral is x minus y magnitude squared. It's the length of the difference signal. If the difference is 0, the distance is 0. Right? If we want to do this with 2 points on the board, if we have x here and we have y here, two vectors with the origin here, there's a vector going like this, a vector like this, then the vector x minus y is this vector, and the distance between the point x and the point y is the length of the vector x minus y, right? So the distance between x and y is the length between x minus y. Like this. Same thing, but with signals, and this using this definition. Okay. So now we have a way of calculating distances between signals, and once we have that, we can compute how close the received signal is to one of the possible transmitted signals, and then we pick that signal alternative which is closest to the received signal. So I'll take that once more. We have the received signal. We can calculate the distance to this signal, and we can calculate the distance to that signal. We need to pick either this one or that one, and we pick the one which is closest to what we have observed, right? So that's the purpose here. And that's called the minimum distance receiver. And that is, in some shape or form, almost always what we want to do in all kinds of physical communication. Okay, so the binary minimum distance receiver works as follows. Remember that we want to make a decision based on our observations. We observe R. So given R, we compute the distance d1, that is the distance between the receipt signal and the first signal alternative. Okay, so what is that? Well, it's the difference between R and S1, and take the norm of it. And this is the square root of the integral from minus infinity to infinity of R minus S1 magnitude squared dt. Okay, so now we have a number, which is the distance of what we have observed to the first signal alternative. And let's calculate then d2 according to the same recipe here. So d2 is the norm of R minus S2, which is the integral from minus infinity to infinity, R minus S2 magnitude squared dt. Okay. Yes?
Is there any particular reason why d2 is squared?
Why we don't square this?
Why we don't square d1 yet we square d2?
My bad. My bad. All right. Sorry. The thing is that, as we see later on, there is no need to take the square roots here. So typically we calculate the distance squared.
Okay.
All right. But thanks. And then, so this is step one. So if d1 is less than d2, then we assign m, our guess on what was transmitted. So m hat is either 1 or 2. What should it be in this case? One or two? What do you think? One, exactly. And why is that?
It's closer to R.
Yeah, so R is closer to S1 than to S2. Therefore, we select S1. And S1 is transmitted if M is equal to 1. Thus, M hat is equal to 1. Okay. And then, of course, if D2 is less than D1, then we do the opposite. That's it. All right. What have I forgotten here? What happens when D1 is equal to D2? Okay. That's no good. We need to specify this also because it could happen. We need to specify all cases, right? What should we do in this case? What should we select M hat to be when D1 is equal to D2?
1 or 2, either way.
1 or 2, either way. Sounds good.
Binary option.
Yeah. I mean, we're maximally unsure about this, right? So let's just flip a coin or just select one. It really doesn't matter. So here, for convenience, we can say, we can just say it can be chosen arbitrarily. For instance, randomly. If we have a random number generator at the receiver, we can run it and then just pick one. Or we could just decide one. Or m hat equals 1. If we don't like that, well, let's take m hat equals 2, right? As we will see, it doesn't matter. I mean, it's a bad situation, right? We basically don't have any information to base our decision on, so we just think of something, right? Okay. So let's take, I hope this was clear. So now we know what to do when we want to transmit one bit. How about if we want to transmit several bits? Well, we use the same recipe actually. It's just that we extend it now to multiple possible transmitted signals. So if we can transmit capital M signals here, so then we have more signal alternatives, S1, S2, up to SM. Okay, and we still have a receipt signal. So what we do is that now we have more choices to choose from, but the principle is the same. We calculate the distance to all our choices and then pick the choice which has the best fit. Right. So we calculate these distances, d sub m for all m, and then we choose the signal alternatives which is closest, which has the lowest value. Okay. In math, it means that we pick m hat as the argument to the min of dm. Okay. Have you seen this type of notation before? Maybe not. So let me explain what I mean by this. Okay, so first the min operator. So we want to minimize dm. Okay, so if we had dm plotted as a function of m, okay, we have a distance, one distance per signal alternative. So we have something for 1, 2, etc. up to capital M, right? And there is one number per possible m here. So maybe we have this as distance, this as distance. They're all positive. And say that we only had 4 signal alternatives to be complete here. So m is equal to 4. So which signal what is the decision we should do in this case? What should m hat be? Should be 1, 2, 3, or 4. Which one should it be? 3, right? And why is that? Yeah, exactly. So maybe I will. So this is the minimum distance, right? Is this number. But we're not interested in the distance per se. We're interested in the index for the smallest distance. So we're interested in this, right? Okay, and how we mathematically say this is that this is the minimum over m, so it's the number, so that's this. However, the arg of this points to the argument that produces the minimum. Okay, so this is the it's the m corresponding to the smallest dm. Okay, if you understand what I mean. Okay. So is it clear? Okay. So the principle here is that the m-ary minimum distance receiver calculate the distances to all the possible alternatives, find the smallest one, and then pick the index of that. And that's our decision. Again, if we have a tie that is one or several, two or several distances are the same, we pick randomly among those, or just pick one of them. That's fine. Okay. Is that clear? Okay. So then we will round off today, and then we will continue on the physical layer stuff on Friday. That is tomorrow. And the purpose is then to talk about, now we have shown how to transmit one bit, or actually several bits here, and then to move this into a more practical setting, how things are done in real life. But the principle is exactly this. Okay, so there's much learned today on a high level.